everyone. This is a continuation of hypothesis test examples that we did in class earlier. So the problem we're looking at now is the gun control problem. So you can pause the video and read the problem to yourself and then unpause it when you're ready to try the problem. And if you would like, you can also try the problem on your own and then compare it to what I write down in the notes. So according to a new NPR Ipsos poll that surveyed both Republicans and Democrats, the percentage of Americans that want more gun regulation has changed since the Parkland, Florida school shooting. NPR reports that in October 2017, 68% of Americans said gun laws should be stricter than they were. Then, after the Parkland shootings in February 2018, NPR, together with Ipsos, conducted a poll and found the percentage had changed to 75%. The poll was based on a random sample of 1,000 adults, with an equal number of Republicans and Democrats in the sample. Conduct a hypothesis test at the 5% level of significance to determine whether the percentage of all Americans who think there should be more gun regulation has changed since the Parkland shootings. Based on the sample, what can you conclude? So the first thing you need to do is determine the hypotheses. So we're going to state the null and the alternative. So the first thing I like to do is put the null. So that's our claim. So in the problem, our claim here is the 68% of Americans said gun laws should be stricter than what they were. So P equals 0.68. My alternative is based on the question. So we're trying to determine whether the percentage of all Americans who think there should be more gun regulation has changed since the Parkland shootings. Changed signifies, is it different? So we're going to have not equal to. So in words, my null hypothesis says that the proportion of Americans who think gun laws should be stricter is 0.08. And my alternative is that the proportion of Americans who think gun laws should be stricter is different than 0.68. For this case, since I'm dealing with a not equal to, I'm going to have a two-tailed test. And the reason it's two-tailed is when we draw our curve, we're going to have a flag on the left and a flag on the right. So we have a right tail and a left tail, so it's two-tailed. Are the conditions for approximate normality met? So we need to check our three conditions. First is random. And in the problem, it says a random sample of 1,000 adults. So that takes care of the randomness. The next thing I need to check is that the sample large enough. So I need to check my 10% condition. So I'm going to take my n, my sample size, which is 1,000, and multiply it by 10, and that gives me 10,000. And all we're saying here is it reasonable enough to assume that there's more than 10,000 Americans? And the answer is yes, adult Americans. And then the last condition I need to check is my success failure. So I'm going to take my n and multiply it by p, which was 0.68, and then I'm going to take n and multiply it by 1 minus p, so 1 minus 0.68 gives me 0.32. And here you get 680, which is obviously greater than or equal to 10. And for the failure, you get 320, which is also greater than or equal to 10. So yes, it's safe to use the normal model or to assume normality. Okay, so to calculate my sample proportion, that's my p hat. And here that's going to be 0.75 because it says they conducted a poll and found the percentage had changed to 75%. So that's going to be 0.75 for p hat. When they asked for the mean, that's my claim. So whatever the hypothesis was, which was 0.68. I also need the standard error of p hat. So that would be the square root of p times 1 minus p over my sample size. And this comes out to 0.0148. When I draw my sampling distribution, like we said earlier, it's two-tailed because it's a not equal to. So my claim, 0.68, goes in the center because that's my mean. And my standard error is going to be 0.0148. So that's how I'm going to calculate my other values. So if I add 0.68 plus 0.0148, it comes to like 0.695. And then if I add 0.0148 to that, I get 0.710. And then going backwards, I'm going to have 0.68 minus 0.0148. So that comes out to 0.665. And then if I keep subtracting, I get that. So that's two standard deviations in either direction. Before I put my flags, let's find the z-score. So to calculate z, I need my value, which in this case was my p hat. So that was 0.75 minus my mean, which is 0.68. And then I'm going to divide that by my standard error, which in this case was 0.0148. And when you do that, you get 4.73. So that's 4 standard deviations in either direction, because remember it's two-tailed. So right now I have 1 standard deviation, 2 standard deviations. So 4 is not even going to be on the graph. It's going to be like somewhere here, and then also the same except on the other side. So if I extend my graph to kind of look like this, what we're really looking for is the area to the right and to the left of the flags, because this is where z equals 4.73, and then equally on the other side it would be where z equals negative 4.73. So again, it's not equal to, so it could be greater than that or it could be less than that. Is my test statistic unusual? Yes, it is, because it's more than 2 standard errors from the mean. Okay, we're going to find our p-value. So to do that, we're going to take normal CDF. Actually, let's write it like this. We're trying to find the probability that z is greater than 4.73, but there's 2 4.73s. There's one to the right and one to the left. So I have to multiply my answer by 2. So when I do normal CDF, I have to also remember to multiply that by 2. So what I do is I choose one of the z-scores. So I'll probably choose this one right here and just base it off of that. So my lower bound, if I look at that one, would be 4.73, and my upper bound would be 100. But remember, there's another area on the left side that's the same, so I have to multiply that by 2. So when you type it into your calculator, be really careful. When you do a two-tailed test, you want to make sure you multiply normal CDF by 2. So pick one side of the curve and then just double your answer. When you type that in, you'll get an answer that looks something like this. So depending on how you rounded, your calculations might be slightly different. When I typed this in, I typed in 4.7 instead of 4.73. When I typed that in, this is what I got. And I discussed this in class on Monday. So when you see an answer like that, that's not 2.6, because remember, our probability can never be greater than 1. That would be wrong. So this is scientific notation, and all this means is 2.6 times 10 to the negative 6th power, which means if you take the number 2.6 blah blah blah, if I move the decimal back 6 places to the left and fill in zeros, that's actually my answer. It's 0.000026, which we would just say is just basically 0. And if you look at the normal model, you can see, I mean, your 4 standard deviations, almost 5 in either direction. The area under the curve at those points is basically going to be 0. So the probability of you obtaining a statistic that extreme or more in either direction is 0%. So kind of think about what that's going to do when we have to determine whether to reject or not reject the null. So right here, that's my p-value. And remember, the p-value is, by definition, it's assuming the hypothesis is true. It's the probability of finding a sample statistic that extreme or more. So, in other words, if I was to assume the null was true, there's a 0% chance that you would find a sample statistic of 75% of the population who would think that the gun laws are strict. So if that's the case, a 0% chance that you would find a sample like that, we're basically just going to throw the null away. Like it's not going to very likely be true. So we're going to end up rejecting it. So how do we tell when to reject it? It says compare the p-value above to the level of significance. Again, your level of significance is alpha, and we're using 0.05 for that. So because my p-value, which is 0, is less than my alpha level, 0.05, I'm going to reject the null. Again, we're saying if the null was true, there'd be a 0% chance you would obtain a sample statistic of 75% or more extreme. So it's very unlikely. So now we're going to interpret the decision in the context of the problem. So the way I want you to interpret that is just say something like, since your p-value is less than alpha equals 0.05, we're going to reject the null. Anytime you reject the null, you would say there is strong evidence, and in this case, there's very strong evidence because it's basically 0. So there is very strong evidence to suggest, again, it doesn't prove anything, we're suggesting, to suggest what? Always refer back to the alternative. So my alternative said the proportion of Americans that think gun laws should be stricter is different than 0.68. So there's very strong evidence to suggest the proportion of Americans who think gun laws should be stricter is greater than, or is different than 0.68. So it could be more than 68%, or it could be less than 68%. That's all we're saying. We're just saying that the null is very likely to be untrue because our p-value is so small. So anytime the p-value is less than your alpha level, you would reject the null. If we had ended up not rejecting the null, then there wouldn't be strong evidence in favor of the alternative. All right, I hope you all enjoy the rest of your day or night. And if you have any questions, please feel free to ask me on Wednesday. We'll continue looking at hypothesis tests, but we'll look at what happens when we make an error with our conclusion, because it does happen from time to time, especially when your p-value is really close to 0.05. Then it's like, okay, you got to make a call. Are you rejecting or are you not rejecting? All right. Hope you all have a great rest of your day.